Okay, we're back. I'm going to pick up with the transition again. I'm going to really have to hit the high points of things. I've fallen a little bit behind, and we're going to end just a couple minutes ahead. So I'm going to just try to make you aware of all the things here and just hit the high points. Another form of instability is due to concave surfaces. It's called a Gortler instability. It's really driven by the radius of curvature. Surface roughness is another contributor to transition. Typically, it's a function of the roughness, and if it's less than a certain value, it'll be smooth. Nose bluntness can contribute to transition and actually have favorable benefits and delay transition of a boundary layer. Boundary layer transition impacts a number of things on the plane: drag, heat transfer, and going from a value of 300 of R theta over M to 150, and for instance, changes our inlet efficiency by 0.25%. And as indicated earlier, 0.25% is quite a bit. Shows some of the data similar to what Mark Lewis showed here for transition. Here there's a couple of interesting points though. Again, there's that wind tunnel data. Here we see the first mode transition being dominant at lower Mach numbers. And then the second mode, cooled wall, actually picking up at higher Mach numbers. Here's over to the right, you'll see a pretty big scatter in RE theta over Mach number, which tends to indicate that it may not be a real great criteria to use. And then down at the bottom of the page, just illustrates the bluntness effect on transition, where here on a blunt limit, you transition later than the sharp limit of a cone. And in between this blunt limit, you can actually get some quite appreciable delay in transitions due to the reduction in local Reynolds number due to the entropy layer being formed by the blunt body. Just keep the camera down here, please, if you can, because I'm going to have to go through some of these very fast. This is a chart that discusses force accounting options. Get into this thrust to drag ratio. What's thrust, what's drag? I'll make one quick point. At high speeds, the whole undersurface of the vehicle is part of the propulsion system, and it makes most sense to account for thrust from nose to tail. Inlet efficiency, different efficiency parameters, very briefly. Mass flow per unit drag is an interesting parameter to look at. I derive that in the next couple of pages, why it's important. A to KE has been discussed for inlets, and there are a whole host of other parameters that can be used, and they're derived and explored in reference 26. Combustion efficiency is mixing efficiency, mixing of fuel and air, and kinetics efficiency, how much that's mixed is burned. Nozzle is how much of your thrust you generate, how much of the ideal thrust. Ideal thrust is what you'd get if you isentropically expanded the flow to ambient pressure. I've got three pages that aren't in the original notes, but you can get in the final set for Mann-Hawker, that develop why thrust to drag ratio is an important parameter and how you can use it to dictate a good or a bad design. Interesting, that parameter in itself you can't use. It has to be used in conjunction with a constraint, like constraining the contraction ratio or the pressure that you compress the flow down to. But if you put in those realistic constraints, it becomes very meaningful. An illustration of that is you can have a flat plate with no compression. It has a very high, a very low drag to mass flow ratio, but you haven't compressed it, so it's not very useful. Forebody and inlet considerations versus Mach number. We've talked about low speed. High speed is mass capture, compression efficiency, boundary layer transition, uniformity. We've talked about flow separations, corner flows, leading edge heating, Dr. Lewis talked about, and the contraction ratio that's optimum to operate at. I already mentioned that we use this Oswitich focused shock inlet design approach. This is discussed in reference 19 as why that's optimal. It tends to produce a minimum total pressure loss for a given amount of compression. The advantages, it has high performance on design and good mass capture. You can cancel all the shocks, so you have very uniform flow into the combustor, but it's also it is point design and sensitive to being off design, similar to a wave rider. Disadvantages, it's only on design at 1 Mach. It spills flow, which you'll see in the next chart, at lower Mach numbers. And sometimes the shocks can coalesce into strong shocks that could be a problem. This just illustrates the 2 conditions on design where all the shocks are coalescing to points here. This is a case, we didn't have this in our design where we upturned the cowl to reduce the strength of the inlet shocks, but in the actual design you could take advantage of that. Down below shows the off design where you're at lower Mach numbers. All these shocks now not going, the ramp shocks, the fact that they're not going inside the inlet means that they are spilling flow, pushing flow around the cowl. In other words, you've pushed flow through these shocks and compressed it, but it's not going through the engine to produce thrust. That's called spillage drag. Okay, on our baseline design, I picked 3 body ramps plus 1 cowl ramp. Shock on lip Mach number at 15, that's when this bow shock goes on the lip, and a contraction ratio of 40. Down here shows trends of inlet efficiency as a function of the initial 4-body angle. You can see as you go to lower angles, you get higher efficiency. And then for a given 4-body angle, how it changes with contraction ratio. Higher contraction ratio is producing less efficiency, but there's a trade-off here. You might have less inlet efficiency, but you have lower Mach numbers to add heat to. One design option for inlets is 3-dimensional design, where Dr. Lewis mentioned this, where you compress sideways as well as vertically. NASA Langley basically came up with this concept. 3-dimensional compression tends to reduce the strength of shocks. A good rule of thumb is keep angles smaller than about 6 degrees, which is very hard to do in a 2D design. We didn't do it in ours. It's also, they tend to be fixed geometry, which reduces weight and complexity, and the leading edges are swept to reduce heating. And at low speeds, that swept leading edge actually pushes flow down out of the engine and helps spill flow. Spilling flow at low speeds can help the inlet to start. Here is shown for a Langley inlet concept some of the performance parameters like inlet capture and inlet contraction ratio, throat Mach number, and total pressure recovery as a function of Mach number, just to give you an idea of how that kind of an inlet performs. Mark Lewis talked about this extensively, and even showed the same data, but just that issue of the cowl leading edge, I'll just add that our design is Mach 15 shock on lip. If we designed it so that the shock never went on the lip, you'd always be spilling flow and you'd have low performance. So at some point you will have to deal with the shock, bow shock, passing across, and ramp shocks crossing the leading edge and the heating associated with that. Combustor, moving on to the combustor component. Combustor inlet interactions are important. Thermal choking we've talked about, fuel air mixing at low speeds, ignition delay, flame holding, transitioning from one mode to another. At high speeds, mixing efficiency and the losses incurred to mix fuel and air. Heat transfer is an issue. Chemical kinetics. Here it's not an issue of igniting the flow, but driving it toward equilibrium. If you burn it but don't bring it towards equilibrium, you'll lose a lot of thrust. And then shock and friction losses inside the combustor. Mixing efficiency. How do you determine what the mixing of fuel and air is? How is it driven by geometry and flow conditions? Griff Anderson from NASA Langley, from a large base of data, has established mixing correlations for both parallel injection, injecting along the direction of the flow, and perpendicular injection, which is injecting normal to the flow. I'll just point out those relationships there. That's why I chose a combustor height of 2 inches. So I wanted to look at attempting to inject fuel exclusively from the wall, which avoids putting injectors or struts into the flow, which can create a lot of losses. So I picked 2 inches. This resulted in a required combustor length of 64 inches when you're running stoichiometrically for a combustion efficiency of 90% and perpendicular injection. Anticipating mixing enhancement schemes like Dr. Lewis talked about, I just said let's reduce that by 30% and pick 48 inches. That's very important. The combustor length is probably one of the key drivers of the vehicle. It's very heavy because of the high pressures and the fact that it has to be cooled, and it creates a tremendous amount of heat load and friction drag. Heat load goes roughly as pressure, and so you get tremendous losses there, and if you don't control that length, it can be a problem. Now, what about angling the fuel instead of injecting it normally? This is just some data by Chuck McClinton taken at NASA Langley, which is a little hard to see, but what it points out is that the penetration of the fuel into the air can actually be increased. These lines up at the top here for the penetration of the fuel with the air and the maximum concentration of the fuel in the air, the height of maximum concentration, actually increase with lower angles. So, and at 30 degrees it was better than 90 degrees. So we've picked 30 degrees for our baseline design, angling the fuel at 30 degrees. Fuel penetration, since you're trying to inject from the walls, the only way you're going to get it to mix is to get that fuel out into the airstream. Again, you can do it artificially with structure or struts or something, or you can just try to inject a jet. Penetrating a fuel into the stream is a function of a number of things. Jet static pressure at the injection point, its Mach number there, the jet diameter, its injection angle, cross flow Mach number, that's the main flow Mach number and static pressure, and then the oncoming boundary layer thickness. And illustrated here are just 3 or 4 different physical possibilities for injecting the flow: thick boundary layers versus thin boundary layers, match static pressures versus under expanded jets. And this reference I show at the bottom and over to the left have methods for actually calculating the amount of penetration. Dr. Lewis also talked about this, the effects of supersonic flow or compressibility on mixing. It has been shown experimentally that shear layer growth. Now, if we try to inject our fuel axially or even normally, because eventually that jet turns over and you start to mix along shear layers. Shear layers are layers where the velocity, there's a velocity difference across, it's a stratified flow and you have velocity differences. One of the primary mechanisms for mixing in a combustor is turbulence, turbulent diffusion, and that's really about the only way you're going to get it to mix in the time you've got to mix it. And this so-called convective Mach number effect dramatically impacts the amount of spreading rate of that shear layer, how it grows and mixes with the air. The relationships that define convective Mach number are shown. You can get, dig into that deeper. Basically, though, convective Mach number is a Mach number of each one of the flows, the primary and secondary flows, relative to a convective velocity. Convective velocity is the velocity that large-scale structures like vortices are traveling along in the flow. And the way you determine what that convective velocity is determine at what velocity do you have to be traveling such that the two flows stagnating into that point have the same total pressure. That's called a saddle stagnation point. It's illustrated here in the drawing. And it's, again, the velocities relative to that determine what the convective Mach number is, and it's a measure of compressibility. The higher convective Mach numbers, if you go to the right, shows that higher convective Mach numbers decrease the shear layer growth rate relative to the incompressible value, which the ratio at low speeds or incompressible is 1, and it decreases with Mach number. Very important consideration. Dr. Lewis mentioned mixing and enhancement and the introduction of vorticity through shocks. There are also other ways of doing it shown in the literature. Bert Northam at NASA Langley has introduced swept wedges, where the flow coming off of these swept wedges introduces vorticity, and is shown to the right in this mixing efficiency. The swept ramp does produce more mixing efficiency as a function of length than either injecting from the wall or from a non-swept ramp. Down below, Swithenbank has this idea of an acoustic reflector to introduce noise, turbulence into the flow, and to the right shows how the vortex generator increases mixing. The acoustic reflector shows the concentration going down and it's spreading out. Here's an interesting issue. Swithenbank from England brings up quite a bit. Do you ever get to a point where trying to mix fuel is you lose more than you gain? Okay, you have to generate turbulence to mix the flow, as I mentioned. Generating turbulence requires drag, basically, to do it. You know, those wedges would create drag, a reflector would create drag, walls create. If you just inject it axially and you want more mixing, you have to make your combustor longer. So it's, that turbulence is you pay drag for that. I'll move on here. I did an analytical study on a simple case shown here where we injected fuel parallel in our combustor and then looked at 4 different levels of mixing efficiency at a Mach number of 18, free stream Mach number of 18. And so the combustor length was set to establish these 4 levels using Griff-Anderson's mixing correlations. The NASA Langley program SCRAM was used. Jim Walton helped me out with that. Was used to do this analysis. It also included turbulence. Turbulence was a key part of this. So I basically referred to test data to get the levels of turbulence in the duct, and I used a simplification of the K-epsilon turbulence model to establish the rate of turbulence damping as you go into the nozzle. In the nozzle, in a highly expanding flow, there's a strong tendency to damp out the turbulence. Okay, this just shows some test data of turbulence intensity in a shear layer. It's data taken on actual shear layers for the purpose of looking at scramjet engines. And I did a normal distribution to this data to find the turbulent kinetic energy, which is defined as the turbulent fluctuation velocity squared over 2. And got a reasonable fit. You can see by those plots that they do look somewhat like a normal distribution. In practice, I just used the maximum value of 0.005 for the turbulent kinetic energy in the analysis. Similarly, the dissipation of turbulence is a function of the length scale of the turbulence, how big the turbulent eddies are. Again, referred to data by Schetz and others at Virginia to establish what those mixing lengths were, and in fact they correlated pretty well to mixing length hypothesis. When all that was turned into analysis, I found that for this Mach 18 condition, that we reduced our mixing efficiency as we went to the lower mixing efficiencies. It was still beneficial to keep your mixing efficiency high. That may not be true if you do other means, you know, if you try to increase the mixing by putting in wedges or anything else, but for this particular case it did. Combustor issues related to the kinetics. There are really 2. One's ignition delay, how long it takes for the fuel to react. Ignition delay is driven by the formation of radicals. Initially you get a large spike in radicals like OH forming, and when they have come up to about a peak level, then ignition is said to have taken place, and after that you just have equilibration of the flow. That's the reaction time shown at the bottom. These are 2 correlations you can use as a function of pressure and temperature to establish what they are, and to the right just shows some experimental data and calculated results similar to what Dr. Lewis showed. Probably one of the key issues, and I would take this to heart in the flow path, is thermal balance, or balancing the heat transfer to the skin with cooling requirements. Okay, high heat fluxes do exist in the scramjet inlet, combustor, and nozzle, typically dictate the need for actively cooling the walls using your cold fuel to do so. Hydrogen does have a tremendous heat capacity, so it's very good for doing that. Plus, if you put the energy into the fuel, you get that energy back. That's what regenerative means. That energy you'll get back into your propulsive stream and contribute to thrust. Now there's a downside to this. If you have to cool too much, your fuel levels will rise above stoichiometric values, and eventually you'll get to the point where putting that energy back into the fuel is not a benefit, and it hurts you. So there's a careful balance there. Down at the bottom shows typical levels of the heat sink or the heat fluxes in the inlet, fuel struts, combustor, and nozzle up to Mach 10, showing that up to Mach 10 you might be able to still run at you haven't put enough heat into the fuel where you have to run the fuel higher than stoichiometric, but at higher Mach numbers that will not be the case. Now one way you can help this problem is by something called film cooling. Film cooling is injecting a layer of whatever of cool flow against the wall. In this case, you could use your fuel. So injection of hydrogen against the wall will significantly reduce the heat transfer to the wall and the friction drag on the wall, both of which can improve performance. Plus, it'll also mix with the flow to a degree and add to combustion efficiency. Down at the bottom on the left, you show some pretty recent data compared to old data of this efficiency, cooling efficiency of the film. Basically, at a value of 1 here, there's no heat transfer to the wall, just to give you a feel for this plot. And you see this big difference, and you have to ask why. Well, that's based on an old correlation. If you move to the right and you put some additional physical terms into the correlation, you can see that the data collapses fairly well. That's data from Mike Holden. We'll move into the nozzle now. Nozzle considerations versus Mach number. Low speed, we've pretty much talked about all those. High speed, you really have to optimize, strike a balance between the losses. There are a lot of them: divergence, friction drag, underexpansion, finite rate chemistry. We'll talk about those more in a minute. Interacting with the free stream, heat transfer, profiles coming out of the combustor can dramatically impact your nozzle performance. Viscous interactions, relaminarization I'll talk about, and the fact that the nozzle really produces a lot of the lift at high speeds and needs to produce it, optimally produces lift. Okay, the nozzle efficiency and loss mechanisms, again, we have to carefully balance them. An illustration of this is shown, discussed here. If you want low divergence losses, what are divergence losses? They're flow angularity. Any angularity you introduce into the nozzle flow results in something that's not thrust. Remember, Mark mentioned, Dr. Lewis mentioned that thrust is m dot v. Well, if that v is pointed in the wrong direction, it's not thrust, it's lift or negative lift or whatever. Those are divergence losses. To reduce those completely, you could have a perfect nozzle, which basically is designed to orient all the flow axially. However, perfect nozzles at high Mach number conditions tend to be very long. They have a lot of friction drag, and basically you'll have more friction drag than you get a gain in divergence losses. Another one is kinetics losses. Kinetics losses are, no matter what, at high speed you're going to dissociate. Your temperatures are going to be such that you dissociate a certain fraction of the water that you form due to combustion. If those water fragments don't recombine in the nozzle, you've lost that energy and it will not be thrust. Those are called kinetic losses. And it's hard to get those to recombine in the nozzle. The flow is so rapid and the temperature drops so quickly that they don't, and the pressure drops, so quickly that they don't have a chance to recombine. So a gradual expansion in the nozzle could help that. It would keep your pressure gradient low. It would help to recombine, but then your friction drag will be higher. So there's definite trade-offs there. Here I've illustrated all the different losses, friction and heat losses, the fact that you're underexpanded, your pressure is quite a bit higher than ambient, as I illustrated earlier, divergence losses having to do with the velocity. And down below here show typical values of the kind of losses you'll get in a practical design. Divergence, CFG losses of 0.5 to 1%, underexpansion 0 to 0.5%, friction 1 to 2%. As you can see, that's one of the biggest components to it. And kinetics are 0.5 to 1%. The nozzle, starting in the combustor, because of how noisy it is and the Reynolds numbers and so forth, you'll almost always have turbulent flow in the combustor and into the nozzle. Just point this out. This is a modern, fairly recent kinetics rate package. It's in the literature. I've got it here for your purposes and use. Just something that is necessary when you do, especially nozzle analyses, and cannot assume that equilibrium occurs in the nozzle. This is some work done at Los Alamos showing what are the most important or sensitive reactions in the nozzle, the ones that you really got to be concerned about. And what it points out is for three different levels of phi, or equivalence ratio, one being stoichiometric. Under fuel-rich conditions, a phi of 3, the most sensitive reaction is hydrogen plus a third body going back to hydrogen. Okay. For stoichiometric mixtures, it's H plus OH going to water. That's the most sensitive of the three. And then for lean mixtures, which are really pretty irrelevant at high speeds because you're never going to operate lean, it's OH plus H. Just gives you an idea of what the key reactions, the ones you've got to focus on. Those are the ones where you're losing energy. This is a very useful parameter for establishing the amount of useful energy you got out of your flow. It's called energy yield, and it's the summation of your mole fractions of each of your species times the molar enthalpy of formation divided by the ideal amount that you'd get, ideal amount of water that you would get if you burned at a low enough temperature that it didn't dissociate, times this molar enthalpy of formation. If this is number is 1, you've gotten all your energy out of your fuel. It's not tied up in dissociation. Down in the lower left here, for a given, this is just for a simplistic nozzle design, a straight-walled nozzle design. So these folks at Los Alamos, this is in the AAA journal, by the way, have done a finite rate analysis in the combustor and the nozzle compared to an equilibrium analysis. And they basically showed, this is the sum of radical fractions and the energy yield. I'll look down here at the energy yield. They showed that by the end of the combustor, for their conditions, their Mach 15 conditions, the flow equilibrated, no problem. But now let's go into the nozzle. The equilibrium solution, dramatic, if you assumed that it was going to be an equilibrium, you would get very high energy yields up to almost 1 at the end, whereas the finite rate solution, you got almost no energy yield in addition to what you got in the combustor. That points out the importance of controlling the temperature in the combustor and then trying to design the nozzle to get as much back as possible. To the right are the sensitivities of this energy yield to static pressure, and then after that to temperature. The higher the static pressures, the higher your energy yields, and then to the right, if you move to the right, the higher the temperatures, the lower your energy yield. And those are important considerations in the optimization of the flow path. Viscous interaction. This is an interesting phenomena that I've never really seen reference to in a nozzle, not in this way. Classically, it's either shock boundary layer interaction or leading edge drag, which Dr. Lewis talked about. There also appears to be an interesting one in the nozzle. In Hill and Peterson, classical propulsion textbook, it illustrates how in a convergent divergent nozzle, independent of what the upstream boundary layer thickness is, when you go around the throat and into the nozzle, the boundary layer thickness is pretty independent of what was upstream. It sort of loses that upstream history. And in fact, the slope is about the same as if you had no boundary layer at all. And in fact, I have observed by experience that independent of what the boundary layer thickness is in a scramjet engine, when you go around the corner, the starting friction drags tend to be about the same. It's like the boundary layer starting all over again. So I thought, aha, if it's starting all over again, it's like a sharp leading edge. So I thought it might be similar to the classical viscous interaction. Well, I checked the old chi-bar parameter that Dr. Lewis talked about, I'm sure Dr. Anderson talked about yesterday, and it was much, much less than 3 both before and after. In fact, the parameter didn't change before or after the turn, not significantly. So it's not a classical type of boundary layer growth going on there, but it still has to do with the boundary layer. Dr. Lewis mentioned that the low density flow in the boundary layer. Another interesting point about the boundary layer is that it's very high Mach number in a hypersonic flow. There are very little of the boundary layer is subsonic. It's mostly supersonic. The average Mach number is supersonic, but it's at a lower Mach number than the free stream or core flow outside of it. Because of that, going through a turn, the pressure drop, you can look at Prandtl-Meyer theory to calculate this, the pressure drop is quite a bit lower than what the core flow would be. Now, these two have to match pressure when they go around that corner. And the way they do that is that the core flow cannot turn through as large an angle. Okay? So it turns through less of an angle, the pressure's higher, and that higher pressure now is not drag, because now we're on a forward-facing surface, now we have thrust. Okay? Now this will only be maintained if the boundary layer growth can keep up with this divergence up here. And when the core flow goes around the corner, it's moving away from the wall, which obviously can't be maintained unless the boundary layer can grow to meet it. took a case at Mach 16, just sort of a generic case, that had these conditions in a corner of 22 degrees, and it predicted, this theory predicted that we'd have 34% higher pressures around the turn than if it was in viscid. Now here's a PNS solution in this generic nozzle, both this PNS solution shown at the top and a method of characteristics in viscid solution at the bottom. The method of characteristics solution just shows the rapid drop in pressure as you go around the sharp corner, followed by a gradual rise. This is due to recombination kinetics, actually. It would be flat if it were a frozen flow or a perfect gas flow. And then this is the PNS solution, and as you can see, as you go right around the corner, there's our 134% line drawn across there, and indeed, the PNS, parabolized Navier-Stokes, it's a Navier-Stokes solution, showed this higher pressure going around the corner, which equates to thrust. Now, it appears that the boundary layer growth was not able to keep up with it, and it actually squashed the boundary layer down. The free stream flow had to turn back again to be parallel to the wall, but then as the boundary layer growth does pick up, that interaction and that pressure increase redevelops and then sort of continues down the nozzle. Very interesting phenomena. This is on the whole entire nozzle, what the pressure distributions look like, and as the net effect at Mach 16 was about a 10% increase in pressure thrust, and which corresponds also to a little bit of an increase in friction drag, because friction drag tends to also scale with static pressure. But since thrust is higher than the friction drag, you do get a net benefit out of that. Relaminarization was mentioned earlier and talked about. Experiments have demonstrated that in rapidly accelerating flows, a turbulent boundary layer can relaminarize, or at least the sublayer, the part near the wall, can relaminarize, which could, and a scramjet nozzle will do just that. You know, it's a rapid expansion. So it may produce the proper flow environment. This will produce significant reductions in heat transfer and friction drag. This test data has shown that for this so-called acceleration parameter here, values of 2 to 3 times 10 to the minus 6, values greater than that, did indicate relaminarizing flow. Below that is another correlation derived by different authors of what it takes to relaminarize the flow, and it's a function of the pressure drop across the corner divided by the shear stress, as a function of the shear stress upstream of the corner. It just shows that if the values are up here, it'll revert to a laminar. If they're down here, it will not. And all that can be delved into at your leisure. This shows some more recent test data, a fluidyne test conducted by McDonnell Douglas, and some CFD analysis. And the test data is shown by the symbols, and the CFD analysis is from this GASP code. Turbulent, it was run turbulent, and it was run laminar. And it's interesting that the CFD solution matches the data when it's laminar right around the corner. Now you'll notice that the data also starts to rise as you go aft, and it looks like it's approaching the turbulent value of the GASP prediction, perhaps indicating that the flow is now retransitioning back to a turbulent layer. So that could be a very significant effect. Now, what about the trajectory that we fly along in this for this vehicle? This just shows a typical trajectory taken from the literature. It's the one I more or less use for our baseline. It's a 1500 dynamic pressure trajectory, and at some Mach number you pull up and go to orbit. We maintain 1500 PSF up at least through Mach 18 in our design, but that's fairly typical and gives you a good idea of what a trajectory looks like. Zane Pinckney at NASA Langley used a SR-GOAL computer program to analyze our vehicle at several Mach numbers, angles of attack, and for a range of design parameters. I tried to do a parametric study to show how the performance would vary with different inlets and combustor features and nozzle parameters. The 2D analysis does include the four-body inlet, combustor, nozzle, the upper surface of the vehicle, and the external cowl. And that SR-GOAL program evaluates thrust, drag, lift, pitching moment, specific infolds. Basically everything you need to understand the performance of the flow path. This just illustrates very briefly what the different components and the different codes are that go into the analysis. It's a 2D inviscid four-body inlet solution with a boundary layer analysis, an independent boundary layer analysis. a 1D control volume analysis in the combustor with equilibrium chemistry, and then a two-dimensional perfect gas analysis in the nozzle with a decoupled boundary layer. Now, the perfect gas analysis may sound sort of inappropriate after that discussion on kinetics, but as it turns out, perfect gas solution tends to have a performance that falls in between equilibrium and frozen. So it can get you in the ballpark, and you can learn some interesting things from doing those kinds of analyses. We're getting close here. For the sake of time, I'm not going to spend a lot of time delving through all these parametrics, but at your leisure, you can really learn a lot by going through all the parametrics we've developed here and trying to understand what drives the flow path performance, the ISP, the thrust, the drag. Basically, though, if you'd start with the top, we looked at the baseline vehicle at angles of attack of 0 degrees and looked at a range of minus and plus angles of attack. Looked at contraction ratios. Our baseline was 40, of 30 and 50, a little lower and a little higher, different four-body angles, different shock on lip Mach numbers. The capture area, that's just basically the height of the cowl. And I tried to do these in such a way that everything else was separate. These were independent variations. So the capture area was actually varied by let's say that's our four-body, and there's our shock. You can change the capture area for a given length vehicle, say it's that long, by just sliding up and down the shock. There, there, there. It'll give you different capture locations without changing the shock on lip Mach number. Now, if you keep the trailing edge the same at the same point, what will happen is you'll end up with steeper and steeper nozzle angles. And so it's a trade-off between where you place the engine and how much capture you have and the nozzle angles that are optimum and a lot of different things. And you could really get a lot out of just spending time with that. Also looked at nozzle height independently, nozzle length, 20% variations, combining the nozzle length and height together so you slide along the chordal angle. The nozzle cowl length, that's the right here. That's the cowl of the nozzle. The internal portion of the nozzle is dictated by that cowl. There's our nozzle shape. There's the height and its length, and those are the things that were varied, and again, that chordal angle. The inlet efficiency, just independently varying, what if, doing what ifs. What if you could increase or if you decrease the inlet efficiency by 1%, or the nozzle efficiency, what would it do? Or the fuel equivalence ratio you had to operate at, or the combustion efficiency achieved. Different fuel injection angles, fuel temperatures, the dynamic pressure that you're flying at, a different inlet design. Or these last two were very important, thermally balanced. Everything above was done fixing the equivalence ratio at 1 and not trying to thermally balance the system. What that means is that a certain fraction of the heat that went into the airframe was thrown away. There was no attempt to cycle enough fuel through there to capture all that heat. Well, that has the plus side of keeping your fuel flows down. It has the minus side that you tend to throw away a lot of energy. And for that constant area combustor that we've got in our design, we have a lot of combustor heat transfer. So those last two cases actually were the ones that brought the performance up when you actually balanced things thermally, and then especially when you included film cooling, you got some pretty decent performance. These plots are included in the notes that show the effective ISP, that's the whole vehicle, thrust minus drag over fuel flow, for all those variations. And included in those, for reference, are the if any of the parameters change the inlet efficiency and or the nozzle efficiency, they're all indicated. Now, those aren't indicated in the original notes, but there is a copy of those in the additional notes with all those additional inlet and nozzle parameters. And you can work your way and see what helped and what hurt the flow path performance. One biggie here was this inlet performance. I'm sorry, this one's contraction ratio. On the next slide, you can see that just arbitrarily increasing the inlet performance had a dramatic impact on specific impulse, it changed not only the inlet performance by 1%, which was dictated, but it also had a beneficial effect on the nozzle, and the two combined together to produce a very big impact to the plane. The bottom line numbers over here, these are the ones, these are our baseline shape without changing any of these geometric parameters, but both thermally balancing the system and film cooling the combustor. This is the case without film cooling. This one had a phi of about 2.7, I believe. Got it indicated here. No, 2.7, and then the phi dropped to 1.7 by film cooling, and you can see we got pretty reasonable ISPs for that. The remaining charts show the total vehicle lift, nose to tail thrust, upper surface and external drag, and then vehicle moment. And it is interesting to, again, go through those. Now some of those parametrics you see are a little bit misleading. The reason why they're misleading is because, again, they're all not thermally balanced, and so it assumed that a certain amount of the heat transfer was thrown away. A lot of those cases that had very low performance was for that very reason, that a lot of heat transfer was going into the airframe, being completely thrown away, and that once that energy is lost, you don't get it as thrust. It would be interesting to run that same exact trade study again, thermally balancing all the variables. I did it the way I did to try to keep things independent. I'd like to go back and thermally balance each and every case and see how the trends change, and I know a number of them will change. Also, a point on those charts, the moments look like, when I was studying them as I was traveling out, the moments look like they may be incorrect. I'll check that, and I'll include a corrected version of the moments if that is the case with the package, the supplemental material. This is sort of an interesting thing to just reflect on a little bit. This is the ISP, the integrated ISP as you're going from the nose of the vehicle to the tail of the vehicle. Okay, so on your forebody, it's just the force over fuel flow. Well, obviously on the forebody, you're producing nothing but drag. All you're doing is creating negative ISP. In the inlet, you're adding more to that. In the combustor, the combustor doesn't give you thrust, at least not in our parallel-walled combustor. The fuel momentum gives you some thrust, and that can tend to be a very important component to the thrust at high speeds, because you've heated it up, you get a lot of thrust out of the little injectors if you're not injecting it normally. So you can get some thrust out of the combustor, but typically not enough to overcome these high drags. A divergent combustor you could tend to get a little more thrust out of. All the positive ISP comes out of the nozzle, and that really illustrates the importance of having an efficient nozzle and getting as much performance out of that nozzle as possible. Well, here's our baseline vehicle. These are points I actually analyzed for it using Zane Pinckney's solutions down here, and our transonic solution, which I indicated, and then takeoff, which is just the turbojet efficiency, and just connecting it with lines. That's what our ISP versus Mach number looks like. That compares to, you can compare that back to the cycle efficiency. Now these are just for the engines alone. Again, there's this issue, where do you call engine, what do you call airframe? I don't know, and I'm not sure what was assumed in this particular. I think at the high speeds it would be fairest to compare it on a nose to a tail basis. But it's reasonable performance. And then at Mach 24 here, I just used a rocket level. By then, you're essentially out of the atmosphere, you've burned out, and you know you're operating on your rockets. Now, how much propellant did it require, given that level of performance, for our vehicle? Did we hit our 60% mark that we established its size by? Well, we can check that. Going back to Newton's second law, you can derive the rocket equation for an air-breathing engine, and it turns out to be a function of that effective ISP that I just showed you. I won't go through the derivation for time reasons, but what you can do, and it's very simple to write a PC program that does this, is you break your trajectory up into little bite-sized chunks of Mach number, and then you use average ISP levels across those Mach numbers, and you end up with a sum that looks like this, that the weight into orbit equals the takeoff weight times the multiplicative, the product sum of this exponential factor here. These E values are the specific energy of the vehicle. It's V squared plus GH, okay? It's the specific kinetic plus specific potential energy of the vehicle. Very easy to do that. Well, we did it for our vehicle, and the propellant fraction actually came out to be 0.66, okay? Not the 0.6 that we originally, using the simplistic methods, approximate methods of Jones and Donaldson, determined were there. This shows the importance of the different flight regimes. The sensitivity, this is the percentage delta in propellant fraction divided by percentage delta in ISP. How sensitive is the propellant fraction required to the performance level? You can see in this transonic regime where we had that high drag, have a fair amount of sensitivity. It actually goes down in the ramjet mode. In the low supersonic scramjet mode, it appears to be the lowest, at least for our vehicle. And then as you go to the higher hypersonic Mach numbers, it just gets more and more sensitive. So if you want to optimize your plane, you have to be concerned about these regimes, and you have to have an overall balance. But here is where the pay dirt is. Just very briefly, you can look at the optimum angle of attack the vehicle wants to fly at. I've done that for our vehicle. It's a function of a number of things that you'll just have to study. It is constrained by equilibrium flight, saying that you might want to optimize your specific impulse, but you also have to make the plane fly in equilibrium, be it an angle of attack such that it's being balanced by vertically in forces. Well, if you do that optimization on ISP, you find that for our vehicle at Mach 15, it actually wants to be a slight negative angle of attack. And the gross thrust vector angle, which is the angle of the gross thrust, that's the momentum coming out of the combustor plus the force, the pressure and friction forces on the nozzle, wants to be at a pretty large angle. Well, since it's at negative angle of attack, we're not getting any aerodynamic lift. All of the lift is coming from our nozzle. And that's very typical that you get either a large fraction, depending on the design, it's going to be a different balance, but our simple design came out, all the lift came from the propulsion system. Here we have a sizing plot. You can go back to Bob Krieger's relationships and determine what the takeoff gross weight of the vehicle will have to be as a function of propellant fraction. And it's called vehicle sizing. And again, with all the parameters for our vehicle and maintaining, like I mentioned before, the unit weight of 3 pounds per square foot, which is very small when you look at his curves and you go to larger vehicles, that does increase. But I ignored that effect just for illustrative purposes. This gives you a curve of propellant fraction required versus takeoff gross weight. Well, then you draw in that was propellant fraction available. You draw in your propellant fraction required, which is 0.66, and it'll indicate to us how big our vehicle is. And this is sort of a strange scale. My plotting program at home just plots things on even increments, but it's somewhere in the like 250,000 pounds, where we started at about 145,000 pounds. So it does have to size up to accommodate that propellant fraction required. This curve can at times also not be flat. It doesn't have to be flat. The vehicle gets bigger, all the aerodynamics, all the propulsion don't necessarily scale, uniformly, and so that propellant fraction required curve could have some slope, but I assumed it didn't. Two last points. Synergy and hypersonic design, very important. Components in a hypersonic vehicle are strongly coupled. One affecting one affects them all, or many of them. Components can generally not be optimized independently. You can't go say, oh, I'm going to make the best inlet in the world, because you'll probably hurt something else, and same thing with everything. A good example is contraction ratio. The optimum contraction ratio, the amount that you squeeze the air down, remember it's the ratio of areas between what it is in the free stream, what it is at the throat, is a function of the inlet efficiency, the Rayleigh losses, heat addition losses, inlet combustor and nozzle heat transfer, which is increased by increasing contraction ratio, therefore the cooling requirements, mixing and combustion efficiency. The farther the walls are apart, the harder it is to get fuel and air to mix. Combustor kinetics, that's equilibration. Nozzle kinetics, higher temperatures mean more dissociation, more losses there. And structural weight of cooling panels. All those things have to be considered just to determine what the optimum contraction ratio is. Bottom line, optimization is a multidisciplinary activity. Last chart, vehicle optimization. Well, a number of methods. This is actually some pretty interesting work. Let's see, their names escaped me. Murthy and Paul Sizz have done some interesting work on energy methods and exergy methods just to optimize the cycle efficiency, and I can refer you to that. But another very interesting approach is multidisciplinary optimization, where all disciplines are incorporated in the design. And the reason this works, I mean, you have to do that anyway, but it's a matter of how you do it. Do you do it coupled or decoupled? And this is an approach developed by Sobieski at Langley for decoupling the system and allowing each of the components or each of the pieces to generate their data independently, to generate their own sensitivities. Give you an example very briefly. What you really want to know is what's the total derivative of takeoff gross weight to ISP at a given Mach number. But that depends on a lot of partial derivatives. Partial derivative of ISP with respect to inlet A to KE, or nozzle C of G, or mixing efficiency, or heat transfer, or cooling flow, or blah, blah, blah. This is a way of decomposing the problem down so that the combustor guy can go in and say, well, what is the sensitivity of my combustion efficiency with inlet this or inlet that? And it's a sort of a nice approach to use for optimization. Optimization is the key to hypersonic design. Synergy is the key to hypersonic design, considering all the disciplines together. I apologize for this being very fast-paced. It would be nice to have a day to just sit and discuss it, go through it more interactively with the audience. But I wanted it to be complete, to address all the issues. Some of the remaining charts can be received, and I think it'll give you sort of a design package that gets to the heart of all both the design considerations and the physics that dictate a hypersonic design. I think with that, I'm supposed to turn the time over to Dr. Anderson for a second.
I'm just going to stand here beside you.
Okay.
I simply want to thank all of you here in the live audience, as well as those in the remote sites, for joining us for this course. Once again, I hope that we've achieved, at least in part, our goal, that you are now going to walk out a little bit more mature about aspects of hypersonic aerodynamics and vehicle and considerations, applied aspects. I wish all of you the best of success and just wish you happy trails. That's it. Thank you. You went through it.